Welcome to this explainer. Today, we're taking a pretty wild journey. We're going from the absolutely microscopic all the way up to the macroscopic, literally starting with a tiny piece of embedded silicon and scaling all the way up to global, massive cloud processing. We're decoding Smart Tech 2026 from chip to market. Let's get right into it.
But before we actually get our hands dirty with the hardware, we need to grasp the sheer gravity of this shift. Former Cisco CEO John Chambers put it perfectly. He noted, "The Internet of Everything will be 5 to 10 times more impactful in the next decade than the entire Internet has been to date." I mean, just think about that for a second. The IoT isn't some far-off sci-fi concept anymore. It's the defining technology shift of our era. It's exactly what happens when our everyday things finally start to, well, think.
And the numbers backing this up are just staggering. Looking at the evolution of the internet, back in the web era of 2003, we had about 500 million connected devices. Seems like a lot, right? Well, jump to the social networking boom of 2014, and that number skyrocketed to 11.8 billion. But get this, the projection for the Internet of Things hit 75 billion connected devices. To put that massive momentum into perspective, we share this planet with roughly 7.6 billion people. That means we're looking at nearly 10 connected devices for every single human being on Earth. Absolutely wild.
To make sense of this massive ecosystem, we're actually going to use the human body as our roadmap for this explainer. We'll start with the Internet of Everything, then move into the anatomy of smart devices. Think of that as the senses and muscles. From there, we'll prototype the physical web, which is our local brain. Then we'll connect the nervous system. And finally, we'll zoom all the way out to cloud data and analytics, the global hive mind.
Okay, let's dive into the absolute smallest physical level of our tech stack. Section 2, Anatomy of Smart Devices, focusing on the senses and muscles.
This brings us right to the CASC architecture. This is the fundamental physical loop that actually gives a smart device its intelligence. It really boils down to 4 key steps: sensing, computing, actuation, and communication. First up, sensors collect real-world data, things like temperature or motion. Next, the local processor takes that data and computes it. Then, the actuators kick in. These act like the physical muscles of the device, actively responding to whatever decisions were just computed. And finally, the communication block sends those results out to the broader network. It's just a really elegant, continuous loop of physical interaction.
Let's step up from the senses and talk about local processing. Section 3, Prototyping the Physical Web, our local brain.
So, the crucial thing to understand here is the difference between the 2 main types of brains we use to prototype these devices: microcontrollers versus microprocessors. A microcontroller, like the AVR family, which includes your AT-Tinys or AT-Megas, is literally a tiny computer integrated entirely onto a single self-contained chip. It packs the processor, the memory, and the input-output pins all into one embedded unit. A microprocessor, on the other hand, packs way more processing punch, but it actually requires external components, like RAM and program memory, just to function at all.
And we can actually see this physical difference perfectly in the real world. Think about the Arduino family, boards like the Uno, the Leonardo, or the Mega. These are built entirely around microcontrollers, and they are absolutely perfect for rapid prototyping of embedded, single-purpose IoT tasks. Then, compare that to a Raspberry Pi. This little guy sits right in the palm of your hand, but it's a credit card-sized single-board computer built around a microprocessor. It runs a full Linux OS, it's got HDMI, networking, it can run completely complex IoT applications all by itself. It's a real game changer.
Let's think a bit more about that Raspberry Pi, specifically its 40-pin GPIO header. That header is literally the magic bridge between the software and the physical world. It allows for direct hardware interfacing. For example, a single pin, like pin 7, can support general digital inputs and outputs for your sensors and actuators. This setup makes it the absolute perfect local brain for real-world home automation. We're talking things like a fire and gas notifier, an energy monitor, or maybe even a runaway dog alert. The physical world just plugs straight into those exact pins.
But hey, a brain needs thoughts, right? And that's exactly where programming languages come in. For the embedded resource-constrained systems we just talked about, C is definitely king. It's a compiled language that operates incredibly close to the metal. It practically matches the raw speed of assembly language, but it gives you much better structure and a really tight code size. Python, though, is an interpreted language. It intentionally hides a lot of that underlying complexity to make programming a whole lot easier. So, while it might not be quite as snappy as C on a tiny chip, it is unequivocally the go-to language for higher-level applications. Think data analytics, machine learning, and heavy numerical computing.
Now that we've got a local brain crunching data, it actually needs to talk to the rest of the body. Section 4, connecting the nervous system through communication.
When we look at communication technologies, there is a massive spectrum to choose from. You've got everything from ultra-short-range NFC to Bluetooth, all the way up to heavy hitters like Wi-Fi and WiMAX. But the key here is understanding the trade-offs. As range and speed go up, like with Wi-Fi pushing 100 megabits over 20 meters, the power consumption naturally spikes too, going from very low to high. So if you're out there designing a battery-operated sensor network, you'd probably skip the Wi-Fi and opt for something like Zigbee or 6LoW WUPAN. Those give you very low power consumption over a solid range of up to hundreds of meters, even if the speed tops out at just 250 kilobits per second. It's really all about picking the right nerve fiber for the right signal.
Now, to make sure all these billions of devices can actually talk to each other uniquely across this nervous system, we rely on IPv6 addressing, and the scale of this is just staggering, 3.4 times 10 to the 38th power. Because IPv6 uses 128-bit addresses instead of the much older 32-bit standard, it opens up this incomprehensibly massive pool of unique addresses. That guarantees that every single IoT device you could possibly imagine, both right now and way, way into the future, can have its own unique identifiable spot on the network.
Keeping all of this complex networking running smoothly requires some highly specialized operating systems. We've got incredibly lightweight options like Contiki and Riot for those super constrained devices, alongside ARM's Mbed, Google's Brillo, and of course full operating systems like Raspbian for Linux boards. But the absolute main takeaway here? Interoperability. Remember, the I in IoT literally stands for Internet. Relying on open standards across all these vastly different platforms is the only way we make this entire massive ecosystem talk to itself seamlessly.
Finally, let's zoom all the way out from the local edge devices and the physical network. Section 5, Cloud Data and Analytics, or as I like to call it, the hive mind.
So, all those billions of edge devices we just talked about are continuously pushing their data up to the cloud. And this generates what we call big data, which is usually defined by the 3 V's. First up is volume. We are rapidly scaling from basic megabytes all the way up to petabytes of massive database storage. Second is velocity. The cloud is constantly ingesting all this data in near real-time, continuous streaming. And third is variety. The cloud has to manage a really messy, massive mix of both structured and unstructured data. We're talking everything from a basic single temperature reading to complex social interactions, raw video feeds, and streaming audio. It's a lot to handle. To actually make sense of that incredibly chaotic flood of data, the cloud relies on a cognitive analytics engine. This operates on a 4-step algorithmic loop: observe, interpret, evaluate, and decide. Sound a little familiar? It should. It beautifully mirrors that physical SCAC architecture we looked at earlier, the whole sensing, computing, actuating, and communicating loop. But now it's happening on a massive global scale to reveal hidden patterns and generate actual, actionable intelligence out of raw data.
Which leaves us with this final, truly provocative thought from our sources. If we are actively building an interconnected world where billions of devices can observe, interpret, evaluate, and decide entirely on their own, will humans even be the primary users of technology in the future? It's a totally fascinating question, and one that completely shifts how we view the smart devices quietly working all around us right now. Thanks so much for joining me on this